Chapter 12, Number 21. Several volcanoes have been observed erupting on the surface of Jupiter's closest Galilean moon, Io. Suppose the material ejected from one of these volcanoes reaches a height of 5 kilometers after being projected straight upward with an initial speed of 134 meters per second. Given that the radius of Io is 1,820 kilometers, A. Outline a strategy that allows you to calculate the mass of Io, and B. Use your strategy to calculate Io's mass. I'm actually going to do this two ways. One, by using the fact that 5 kilometers is not much compared to 1824, so we can basically consider that this is still basically a flat Io, and therefore G is essentially constant. And then I'm going to do it using the stuff from later in the chapter and get the exact answer and see how they differ. So let's start off by drawing our situation. We have a thing launched with speed v0, reaching a height h, and coming to rest, and what we'll do is we'll basically figure out what the local value of G needs to be for this to happen, and then turn that into the equation for the surface gravity to find the actual mass of Io. So we begin with, and again here I'm assuming that 5 kilometers is small enough that Io can be considered basically flat, and therefore the G is essentially constant. So we're just going to do energy conservation calculation, and we're going to say that the energy at the start is the energy at the end. At the start, it has 1/2 times its mass times the velocity initial squared, and at the end, it has its mass times G of Io times the height. No potential energy at the start, no kinetic energy at the end. That cancels out the mass of the volcanic rock, which is good, and we end up with something like G Io is V initial squared over 2h, so it's 134 meters per second, quantity squared, over 2 times 5,000 meters. And we get a G value of 1.7956 meters per second squared, which, based on our 3 sig figs, I should really probably call 1.80 meters per second square. And then we're going to go back and we're going to say, well, where's that coming from? Well, we know the surface gravity on any planet, or moon in this case, is G times the mass of that moon over the size of that moon squared. And we can solve this for M to be G value times R squared over big G, which in this case would be 1.8 meters per second squared times 1,820,000 meters, and that distance needs to be squared, over the 6.67 times 10 to the minus 11 weird units, Newton meter square per kilogram square. Before the big reveal, remember that we got the idea that the surface gravity looks this way because we said that the mass times the G of Io should be the same as the force of gravity, which is G times mass of Io times mass of Io times mass of the thing over the distance separating them, which is just the radius of Io. And so that's where that came from. And when all is said and done, we get 8.94 times 10 to the 22 kilograms, which is about right, and is what the book claims is in fact the correct answer. What if we don't treat Io as being essentially flat? Let's treat it as if it were a real object, which is spherical, and so we end up with a greatly exaggerated picture that looks like this, where now we have it, the distance, it starts at distance r from the center, but it ends at distance r plus h, and we're still going to use energy conservation. But now the energy at the start is going to be 1/2 m v initial squared plus the potential energy, which is minus G mass of Io, mass of our guy, over the distance, which is just r. And then over here, we're going to end up with 0 kinetic, but we end up with, of course, potential energy there. So this is minus G mass of Io, mass of the rock, over the distance, which is now r plus h. Important thing to remember, that the potential energy has this negative sign. That's going to be really, really, really crucial. All right, and then we're just solving for the mass of Io. The first thing we notice as is often the case, the mass of the rock goes out, so that's nice. And so we can do something like bring one guy over to the other side. So maybe we get something like G massive IO over R minus G massive IO over R plus H equals 1/2 mv squared. We're looking for the mass of IO, so I'm going to pull that out. And I'm going to get something like, I'm going to pull out a G as well because it's the same in every term. I get 1 over R minus 1 over R plus H is 1/2 mv0 squared. And I'm happy because the thing on the left turns out to be positive, which is good because it needs to be. And then I can solve over and I'll get the mass of IO, and it's going to be something awful, by the way. Kind of carried some stuff that I shouldn't have. There's no m's here. The little m is canceled out. So we get, I don't know, v0 squared over 2 big G, and then 1 over R minus 1 over R plus H. So not pretty. Once you plug in all those nasty numbers, you end up with 8.94 times 10 to the 22 kilograms. In other words, exactly where we were before. We're definitely out at sort of the 4th or 5th decimal place before we see a difference between this and the original, which justifies the original instinct that we could just have treated G as a constant, little g as a constant. We get away with that because of the incredibly important idea that the ratio of H to R is 5 kilometers over 1,820 kilometers, which is about 0.0027 or something like 0.3%. So the difference is not going to be that much.